Hello, good afternoon everyone. In the previous talk, jb3 have talked about our ARMG package, which was optimized very well on supercomputers and workstations. Here, I will talk another module in the ARMG package, the localized operator module. First, I will show the advantages of localized operators, also show you the accuracy of the localized operators module. Then I will give you examples for the optimization for large systems and the scaling, GPU implementation, and the speed up. Here, the DFT total energy can be expanded in non-orthogonal localized operators. It can be centered around the bound or around the item. These operators are variationally optimized. Therefore, only a very few operators needed. Here is a formula for the expansion of the total energy in functions of the operators. I will not discuss more in detail with this. In our software, in our code, all operations performed on a real space grid with multi-grid acceleration. This will lead a fast convergence rate. The main parts scale linearly with the number of items. Also, we find that unoccupied operators are essential for the accuracy and the convergence. In one literature, they have showed this measure can lead to exactly ON scaling if gap exists. As a result, the optimized operators are dual, non-orthonormal linear functions with optimal decay properties like that way. In the RMG package, the operators or localized operators are optimized self-consistently with the residual correction in this formula. In the bracket is the residual we calculated, and the K is a preconditioner. We use a multi-grid preconditioner to accelerate the convergence. Here I will show you how accurate the localized operators can be. For example, this one is antiferromagnetic nickel oxide with LD plus U. In fact, I think we use PBE plus U. Half the U equals 6.5 for nickel 3D orbitals. We use Harman pseudopotentials and with this configuration, and use 13 orbitals per nickel item and 9 orbitals per oxygen item. For this test, we only use a very small radius, 6.5 Bohr. Usually we will use much bigger one, like 8 or 8.5 or even bigger for the more accurate results. But even with this small radius, you can see the results pretty good. For example, here I list the total energies, Xe energies, and Hubbard energies, band gap, and the magnetizations. In this column is the result from our RMG delocalized, or the main module, the main branch. And this one is from localized orbitals with the radius 6.5. It's a very small one. You can see that total energy difference or other difference is very small. For example, the band gap is same up to fourth digit is nearly identical, and also the magnetization is very, very similar. The difference is very, very small. Here I just show you why the localized operators is needed for some big calculations. For example, if we want to run the nickel oxide with 500 tera item cells, just or bigger, just in some reason you need a very high cutoff. I just estimate for the RMG delocalized, the wave function need more than 1 terabyte storage. While for the RMG localized with this small radius only need 160 gigabytes. Even with a larger radius only need 350. This is 1/3 of the delocalized wave functions. This is another example to show you the accuracy. Still the nickel oxide, antiferromagnetic. but we use different functionals. These are hybrid functionals. Here I just show you the total energy, focal energy, band gap, and the magnetization. You can still see the difference is really, really small. In fact, we can also control the accuracy by increasing the number of orbitals. For example, nickel you can use more, oxygen for sure you can use more. Another is increase the radius of these orbitals. For example, here we only use 6.5. That you can use bigger to get more accurate. The localized orbitals are very, very good in scaling for the quasi one-dimensional system. Here I just show you a silicon nanowire. We can do a few thousand with localized orbitals for this, but here I only show you very small numbers. You can see, for example, here I only use a 4-node on summit. For small system, if you look at this curve, it looks like scaling is no good. But in fact, because you use 4-node, for small system, this is just like extremely large resource for the calculation. Therefore, the data will fit into the cache, and it's very hard to see the linear scaling from the beginning. But when the number of items is bigger than 300, and then you can see the linear scaling. And for sure, there's diagonalization is not scaled linearly now. Also, this will be a CPU-only calculation. This is CPU plus GPU. Overall, we have a 2 times speed up if we use a GPU. This is a profiling of performance for the different parts. Left side is a CPU only, the right side is CPU plus GPU. We have 3 parts. It's efficiently have efficient GPU implementations. They are charge densities, matrix calculations, and residuals. For example, from here you can see this one is the matrix calculations. This will be dramatically reduced in the CPU plus GPU, and the multigrid preconditioner part will pop up. We are currently working on the GPU now, this part. We have another part, it's a CPU only part for the diagonalization. Currently we use Scalapac. This will have a cubic scaling. We will replace with green functions or iterative Jacobi or CG method. Finally, we can lead this part to also a order n scaling and implement it in the GPU. Here's another example. It's a graphene nanocone plus waters. This will have 3,000 items and 12,000 orbitals. This is still relatively not very large for us. We only use 24 nodes on summit. You can see the timing here. The diagonalization is really dominant. It's 70%, others only 30%. Still from here you can see with the GPU implementation for the other part, the diagonalization really need to be improved. Another is if you compare the timing for the localized orbitals, compare our base RMG code for the CPU plus GPU, which one is really well optimized. We need 91 seconds per SCF step, or for this we only need 77 seconds per SCF step. We also implemented time-dependent DFT in the localized orbital modules. The TT-DFT opens opportunities to study absorption spectra for large systems, electric field and laser-induced reactions, and so on. Therefore, it's very useful. The localized orbitals are optimized just before the TT-DFT simulations, and also in the simulation, no diagonalization is needed. For example, here is an example. We show the graphene nanocone plus waters. This have 8,000 electrons, and we use 12,000 orbitals. Here just the primary results for the dipole oscillations after initial electric field kick along the z direction. From these oscillations, we can get the absorption spectrum. Here I just show you the timing on the summit with 24 nodes. You can see the total timing per step, TDFT step, is 37 seconds. It's very good. And the TDFT occupy around 50%, and the Hamiltonian matrix update and the charge density are another 50%. Here is a summary. The localized orbitals are variationally optimized for each atomic configuration. This will lead a very accurate minimal basis set. What the localized orbital can do is a regular electronic structure in DFT. It can also provide tight binding like Hamiltonian with overlap matrix. We also build an interface with quantum currency pack, supplying initial wave functions. The basis set can be used for very large calculations in another RMG module, the non-equilibrium green function module for multi-terminal ballistic quantum transport. It can handle 50,000 items on summit. Here's the functional we can use: LDA, GGA, PBE, and plus U, and also the hybrid functional like this. Thank you very much. Also, please visit our website to download our code and try it.